We all know that digital computers change virtually every aspect of our lives. Well, the arrival of quantum computers could be more historic than that. So, what is a quantum computer? It is the ultimate computer, a computer that computes on electrons, the ultimate constituent of matter itself. But the question is, what can it do? Quantum computers can change everything. The economy, crack almost any code, how we solve problems, the way we interact with the universe. You name it, quantum computers will be there. You see, computers have gone through three basic stages. Stage 1 was the analog computer. About 2000 years ago, on a shipwreck was found the world's first analog computer. It was designed to map the motion of the moon, the sun and planets to simulate the universe. As humans started thriving, they needed to count everything. How many cows they had, how much profit they made, and interest rates. 1,000 years later, Charles Babbage created the ultimate analog computer with hundreds of gears, levers, and pulleys. It could calculate longitudes, latitudes, and even interest rates. Then, in World War II, the analog computer failed to crack German code, so the job was given to mathematician Alan Turing. He codified many computational laws into what we now call as digital computing. It operated on ones and zeros at the speed of electricity. They were basically Turing machines. The next step beyond digital computers are quantum computers. In 1981, physicist Richard Feynman first theorized the creation of quantum computers. In 1998, Jonathan Jones brought that theory to life, showing that the ultimate transistor is an electron. One electron that could control the flow of electricity, not just an on or off, but everything in between. These computers compute on electrons rather than transistors. You may ask, if they're based on electrons, how come they have so much computational power? Because they can be in two places at the same time. That is what gives quantum computers its power. At the fundamental level, quantum mechanics can be reduced down to a cat, showed in this cat. Let's take a box. In the box, you put a cat. And the question is the cat dead or alive? Well, until you open the box, you don't know. It is dead and alive simultaneously. It is in a superposition of two states. The cat can exist in both states simultaneously. In fact, in any number of states simultaneously. The cat could be dead, alive, playing, jumping, sideways, sick in any number of states. Now, why am I mentioning this? Because this summarizes the power of quantum computers. When you measure a qubit, it loses its superposition and collapses into either a simple 0 or 1. It doesn't measure as 0.5. Instead, it has a 50% chance of being a 0 and a 50% chance of being a 1. This is in between state, is why some people say a qubit can be both 0 and 1 at the same time. It also means that a small amount of qubits can represent a large amount of information. In summary, parallel computation gives quantum computing its unique advantage. As we know, bits are very slow, so quantum computers don't use simple zeros and ones. Instead, they use qubits. Qubits can be a 0, a 1, or any combination of the two. This is called superposition. Now, let's talk about gates. Similar to digital computers, we use gates to alter the states of qubits in circuits. For example, a qubit in the state of 0 can be put into a superposition between 0 and 1 using edge gate. Circuits can have multiple qubits and gates. Quantum computing has great potential, but its unique challenges hinder mainstream adoption. There are three main areas that include quantum decoherence, error correction, and scalability. Quantum decoherence. Quantum decoherence is a key challenge in quantum computing. It happens when a quantum system interacts with its environment and loses its quantum properties, turning into a classical state. This transition limits coherence time, which is how long quantum information can be processed and stored. Moreover, maintaining a qubit's coherent state is delicate, similar to balancing principal state, where any small disturbance can cause errors. Quantum error correction. Quantum error correction is essential for quantum computing, but it possesses unique challenges. Unlike classical error correction, quantum error correction must navigate the quantum no-cloning theorem, which prohibits creating identical copies of unknown quantum states. Moreover, quantum errors are more intricate than classical bit errors, as qubits can experience different types of flips. Experimental groups like Google have demonstrated error detection using the surface code, with ongoing efforts to improve reliability and scalability. Nonetheless, achieving fault-tolerant quantum computation where errors don't disrupt computations remain a significant hurdle. Scalability. Scaling quantum computers poses unique challenges compared to classical ones. Unlike classical computers where adding transistors boosts power, quantum computers require all qubits to interact for maximum capability. However, as qubit number increases, maintaining these interactions becomes harder, leading to more errors from factors like noise and imperfections. Yes, the hurdles affecting the growth of quantum computers, but they pale in comparison to the benefits that may be unleashed by quantum computers. We are talking about opening the floodgates. The computer will be able to model diseases at a molecular level and will be able to cure the incurable using quantum computers. We will be able to create a theory of the entire universe, a theory that will include Einstein's theory, a theory that will explain black holes, supernovas and galactic evolution. Now we just need quantum hardware to catch up. Thank you.